Yeah.
Okay.
Can you see me?
Yeah.
Yeah. Can you see the slides?
Yeah, perfect.
They're not full screen yet.
They're not full screen yet.
Not on my screen.
Try Control L.
Control L. How about now?
Yeah, sorry, Apple L. Yeah, Command L.
How about now?
No. It's not a big, if it needs to be like this, it's not a big deal.
Now it's okay, or
No, it's still
okay. Maybe I try to connect with my iPad.
Okay.
Great.
Yeah, that's
Maybe this is better.
Yeah. Hey, Francesco, whenever is good.
Okay. Welcome everybody to this new seminar of the One Word Probability Seminar. It is a pleasure to introduce Rongfeng Sun, a friend and also collaborator from National University of Singapore, who's going to talk about scaling limits of disorder relevant systems. As usual, any question you might have, you're welcome to post it on the chat, and we will try to give answers during the talk. So you can go, Rongfeng.
Okay. Yeah. Thanks for the invitation, and thanks for the introduction. Okay. So I'll talk about scaling limits of disorder relevant systems. So this is sort of an introductory talk for the second talk that Bowditch will give on the random field easy model. So this is just meant to give the background. Okay, so I'll first introduce the general framework of what all this fits in. So basically, the framework we are considering is disorder perturbations of equilibrium statistical physics models. In other words, disorder perturbations of Gibbs measures. So I'll illustrate the notion of disorder relevance versus irrelevance for two models. One is the directed polymer model. The other one is the random field easy model that Adam will talk about in more detail later. Then I will discuss how the continuum and weak disorder limits arises if we take the renormalization point of view. So this fits naturally with scaling and the renormalization. Then I'll discuss how we can actually approach the question of constructing continuum and weak disorder limits. So that is done by partition functions, by considering partition functions and using polynomial chaos expansions for the partition functions, which can then be shown to converge to Wiener chaos expansions. And once you have the limit of the partition functions, then you can try to construct the continuum models, disorder continuum models themselves. So let me start with, it's not the refreshing. Sorry. Okay, so let me start with the directed polymer model. So the directed polymer model is a model that is a change of measure of random walk. So here, X is mean zero random walk on the d-dimensional integer lattice with low p. So what is illustrated here, this is the random walk. So horizontal direction is time, and the vertical direction is space. So a priori, the reference measure we start with, when we don't have disorder, the reference measure we start with is just the random walk. So in this case, a simple symmetric random walk on ZD. It's directed because we plot the space-time trajectory. So one direction is always time. So we think of the time direction as the directed part. Now, for every point on the space-time lattice, we have a random variable omega. So that will be the disorder or the random environment. And the assumption is that the disorder has a mean zero and finite exponential moments for parameters close to zero. So this omegas will be the disorder that will be introduced to change the law of the random walk. So the way we change the law of the random walk is the following. So given a realization of omega, the disorder, the directed polymer on this d-dimensional space, one-dimensional time, is defined by the following family of Gibbs measures. So basically, change of measure with these exponential weights. So the reference measure, the reference probability is given by the probability of the random walk. And then we weigh the trajectory of the random walk up to time n. So we have to fix a time horizon n. So for the trajectory of the random walk up to time n, then we weigh the trajectory of the random walk with exponential factor that is given by beta. Beta is a positive number called the inverse temperature. And beta times this summation here. So the summation is simply the summation of the disorder omega that the random walk sees along its space-time trajectory. So in other words, the change of measure favors trajectories which collect large values of environment, large values of the disorder. So the random walk seeks out the regions with the larger values of omega. And the stronger is the value of beta, the more pronounced this effect is. So when beta is equal to 0, the exponential weight has no effect. You just have the random walk measure. But when beta is equal to infinity, then the measure, the Gibbs measure, actually concentrates on a single trajectory, such that the trajectory maximizes the summation of the omegas, the summation of the weights along this trajectory. And this model actually also has a name. When the beta equal to infinity case, the model is called the last passage percolation. The denominator here, z omega and beta, this is called the partition function. So that depends on the omega, the disorder, depends on the time horizon n, or the length of the polymer, and depends on the inverse temperature beta. So the partition function is an important quantity in the study of these such systems. Now, what is interesting about the directed polymer is that as simple as the description is, the model has a phase transition. So this means that as the beta varies, the model undergoes a change of qualitative behavior for large n. Heuristically, you can see that why this may be the case, because beta affects the strength of the disorder. So it's, as I mentioned, when beta is equal to 0, the disorder has no effect. It's a random walk. So what happens is that when beta is small enough, below a certain critical point, then the polymer measure, the measure of the random walk under the Gibbs measure, is still comparable to the original random walk. But when beta passes a certain critical threshold, then the picture changes. The random walk prefers to seek out the regions far out in space, far out such that it becomes atypical for the random walk to do so. But the disorder is so favorable in these regions that the random walk still prefers to go there. So that is the type of phase transition that we will witness. So this basically, below the critical point, the random walk is diffusive under the Gibbs measure. And in the large n limit, you can prove that it converges to Brownian motion, just like the original random walk. And when beta is larger than the critical value, then the random walk under the Gibbs measure should become super diffusive. Now, this is mostly still a conjecture, and it can only be proved in dimension 1+1 for exactly integrable models. So that is the nature of the phase transition for this model, and many things are still open. Now, what about the value of the critical point? Well, it turns out that in dimension 1 and 2, the critical beta actually is equal to 0. So in other words, as soon as you add disorder to the system, then the polymer or the random walk under the Gibbs measure should become super diffusive. So the critical exponent changes, the diffusive exponent changes from 1/2 to something that is different. So in that sense, the disorder is a relevant perturbation of the original model. The original model is a random walk. It's a relevant perturbation because you just add an arbitrarily small amount of disorder, the large scale behavior changes drastically. So the perturbation is called a relevant perturbation. However, in dimensions 3 and higher, the critical value becomes strictly positive. So you need to make the strength of disorder large enough in order to see this qualitative change of behavior. If the perturbation by the disorder is small, then you still have diffusive behavior. And on large scale, the random walk still converges to the same Brownian motion as the original random walk. So in that sense, the perturbation by disorder is irrelevant because small amount of perturbation does not change the behavior of the model on large scales. So that explains the notion of disorder relevance versus irrelevance for the directed polymer model. Okay, so that's what for the nearest neighbor random walk. And similarly, you can also consider spatial dimension equal to 1, but the random walk is now heavy-tailed, so it has a parallel decay for its tail probability. In particular, if it lies in the domain of attraction of an alpha stable process for some alpha between 0 and 2, then the alpha plays a role of a spatial dimension effectively. So alpha equal to 1 is the point where the random walk changes from transient to recurrence. And in this case, we have a continuous family of parameters that sort of mimics the continuous change of dimension. So disorder in this case is relevant for alpha between 1 and 2. In other words, the critical beta is equal to 0. And disorder is irrelevant for alpha between 0 and 1. So that's the transient regime. So you can see that dimension 2 for the nearest neighbor model is a special. It's a critical dimension. And for the one-dimensional heavy tail case, alpha equal to 1, that is a critical alpha. So these are called the marginal case. So there is a good reference on the directed polymer model by Francisco Metz based on his Sanfula lecture notes in 2016.
Rongfeng, there is a question on the chat. Milton is asking whether non-directed polymers are expected to behave similarly.
Okay, non-directed polymers, if you sort of put a drift on it, so that the random walk has a drift in a certain direction, or if you look at, say, the polymer stopped until the random walk stopped until it hits a hyperplane, then in that case, the behavior should be similar to the directed polymer model. But otherwise, it's a difference.
Okay, thanks.
Okay, so that's the directed polymer model and what is meant by disorder relevance versus irrelevance. Now let me discuss the easy model and how we perturb the easy model with disorder. So the easy model is a classic model for the ferromagnets. So we are going to assume put the plus boundary conditions as always. So we take a subset of a CD. So we take a subset of ZD and then we put the plus boundary condition. So at every lattice site inside omega, you have a spin value, which corresponds to a little magnet that can either point up or down. So if the little magnet is the spin, or the little magnet points upward, then we denote the spin value by +1. If the little magnet denotes points downward, then we denote it by -1. So the spin configuration is given by this collection of sigma x's indexed by the points on the lattice inside omega. So the easy measure is a Gibbs measure defined as follows. So the reference measure here is just the uniform distribution on all plus-minus configurations. And then we introduce interactions through this exponential weight. So if you look at exponential weight, basically, if we look at the first term, then basically it favors configurations where nearest neighbor spins. So x and y here are sum over all nearest neighbor spins. So when nearest neighbor spins point in the same direction, so that this product is equal to +1. So either sigma x, sigma y are both equal to 1, or sigma x, sigma y are both -1. Then you get a positive exponential weight. You get e to the power +1, e to the power beta as the weight. If the nearest neighbor spins point in the opposite direction, then you get e to the power -beta weight. In other words, the first part simply forces the spins to align with each other. And the larger is the value of beta, the more stronger is this effect of alignment. Or the second term is the effect of an external magnetic field. So H is the so-called external field. Namely, I place an extra magnet near my domain, near my omega collection of spins. And the external field points, say, in a certain direction with a strength H. Then it forces the spins at each lattice side to align with the direction H. So if H is positive, then when sigma x is +1, aligned in the same direction, then you pick up positive exponential weight. When sigma x equal to -1, then you pick up a negative exponential weight. So this simply forces the spins to align in the same direction as the external field. So beta, H are respectively the inverse temperature and H, and their strengths indicate the strength of the coupling, the nearest neighbor spin alignment, and the effect of the external field. Again, Z here is the partition function which turns it into a probability measure. And with a partition function, we take the logarithm and then we normalize by the volume, the number of spins in the system, and take the infinite volume limit. That limit defines the so-called free energy of the model. Again, the free energy model is an essential quantity in the study of such equilibrium systems. Okay, so for the easy model, as a model for ferromagnets, there's also phase transition. Basically, for magnets, if you have a magnet and you heat it up, although we never do it, but if you actually do heat it up, then above a certain temperature, the spontaneous magnetization disappears. The magnet loses its magnetism. And this is illustrated by the following quantity. So under the Gibbs measure, we sum up all the spins, and then we take its average, divide by the volume. So this measures the average spin value, the average magnetization of the system under the Gibbs measure. And then we take the infinite volume limit. So that converges to a quantity that is called the magnetization of the system. And it turns out that if we assume that the external field is not present for simplicity, then it turns out that there is a critical inverse temperature beta. So below this critical inverse temperature beta, the coupling between the nearest neighbor spins is not strong enough to force the creation of a spontaneous magnetization. But if the coupling becomes strong enough above the critical temperature, then below the critical temperature or above the critical beta C, sorry, the beta is the inverse temperature, so it's a reciprocal of the temperature. Then you start to have a spontaneous magnetization. Remember that we assume the plus boundary condition. So on the boundary of the domain, all the spins are pointing upward. So therefore, below the critical temperature or above the critical value, the spontaneous magnetization is in the same has the same sign as the boundary spins. And this actually can be captured by the derivative of the free energy with respect to the external field. So that's the phase transition for the magnets, in this case for the easy model. Dimension 2 is very special. So dimension 1, of course, we know that there is no phase transition. Dimension 2 is where you start to have interesting behavior. And in fact, dimension 2, people have computed the exact value of the critical point. It's given by this 1/2 log of 1 plus the square root of 2. So in this case, there's been a lot of work in the study of the two-dimensional easy model, including work by Smirnov and various co-authors. So there's been significant progress in showing that the two-dimensional critical easy model converges to conformally invariant scaling limits. There was a recent work a few years ago by Gamir, Gabon, and Newman, who showed that if you look at the model at the critical temperature, and then you vary the external field. So as we saw that once you have a non-zero external field, then you're going to have a spontaneous magnetization. So what they studied was how does the spontaneous magnetization depend on the external field? And what they discovered was that, what they proved was that as the external field tends to 0, the spontaneous magnetization depends on the external field as h to the power 1/15. So 1/15 here is what we call a critical exponent. So now the question we are interested in is what if we add disorder to the model in the form of a random external field? So we again look at the critical model, but now we perturb the critical model with a random external field. So in this case, the external field will be assigned to each lattice point, to each spin. There will be an independent external field. So the external field is basically given this form: lambda omega x plus h. H is a constant, and then lambda is another constant. Omega x here are assumed to be IID random variables, again with the same assumptions as for the directed polymer. It has mean 0, finite exponential moments for parameters close to 0. And what we do is that we perturb the reference critical easy measure. So this is a critical two-dimensional easy measure at the critical point. And then we change the measure with exponential weight that is given by the interaction between the spins and the random external field. So for every spin, it feels its own external field with mean h and with the randomness given by this omega x. Lambda is the strength of the disorder. So Z is again the partition function for this model, which now depends on the disorder. So we can ask the question whether this disorder perturbation is relevant or not, in the sense that if I put an arbitrary small disorder strength, so I just add some disorder, make sure that lambda is not equal to 0, but the lambda is small. And then I look at how the spontaneous magnetization varies according to the mean of the external field, right? So the mean of the external field is H. When H equal to 0, by symmetry, we expect that the spontaneous magnetization under the disordered system will still be 0. And as you vary H, then the spontaneous magnetization should depend on H in certain way. When there is no randomness, what we saw from Gambier, Gabon, Newman is that the spontaneous magnetization behaves like H to the power 15. But now once you add the disorder to the system, the question is whether disorder perturbation is relevant or not. So if the magnetization behaves again like constant times H to a certain exponent, if that exponent changes from 15, as soon as you add the disorder to the system, no matter how weak it is, then this will suggest that the disorder perturbation is a relevant perturbation. However, if H or gamma, the gamma here is equal to 15, for lambda small enough, it is gamma is always equal to 15, 1 over 15, then disorder perturbation will be irrelevant. So this is what we mean by disorder relevance or irrelevance for this random field perturbation of the critical Ising model. So the conjecture we have is that disorder perturbation always makes the sort of things more smooth. So we expect that the critical exponent to become larger than 1 over 15. Disorder perturbation tends to make the transition more smooth. Okay, so that's the random field perturbation of the critical Ising model and what is meant by disorder relevance versus irrelevance. So these are just the two sample models to illustrate this notion, and this is very general. This notion of disorder relevance versus irrelevance actually is far more general. So our motivation is to connect disorder relevance, irrelevance with scaling limits. So in particular, the notion of disorder relevance can be understood via renormalization group transformation. Or in other words, so that in the common language, it might just mean that we perform coarse graining. So we zoom out, we look at a model. So the original model is on a certain lattice, say a unit lattice spacing. And then we zoom out and look at things on the larger scale. Or equivalently, you make the lattice spacing smaller and smaller. And then you compare this rescaled model with the original model with the lattice spacings of order 1. So what we can see that disorder relevance heuristically means that when you zoom out and you look at you compare it with a model with a lattice spacing of order 1, you'll find that in some sense the effective disorder strength of this rescaled model, of this coarse grained model, will change as you perform this coarse graining over and over again. Disorder relevance simply means that as you keep on performing this coarse graining, the effective strength of disorder blows up. So that's is essentially what is meant by disorder relevance. Well, if disorder is irrelevant, then as you keep on zooming out onto larger and larger scales, or make the lattice spacing smaller and smaller, then what you find is that the effective strength of disorder basically vanishes, which explains why on large scales, if the disorder perturbation is irrelevant, then small amount of disorder has no effect on larger space-time scales. There is a borderline case, which is called a marginal. So the notion of relevance, irrelevance is connected to dynamical systems. Basically, with the way people think about it is that we are looking at a dynamical system on the space of models. So that's the whole renormalization group theory. So the iteration on the space of model is given by this coarse graining operation. Just like a dynamical system, if you have a fixed point and you move a little bit away from the fixed point by a perturbation, so in this case, the perturbation is given by introducing disorder. Now, for dynamical system, if you perturb it around the fixed point in the direction that is unstable, then what you see is that if you keep on iterating the dynamical system, then it will just move away from the fixed point. And so that basically corresponds to disorder relevance. We perturb the model with disorder. If disorder is a relevant perturbation, then as you keep on looking at things on larger scales, you find the model will look more and more different from the original model. And disorder irrelevance means that you are perturbing the dynamical system in the space of models in the direction that is stable. So that is a heuristic. So there is a simple model, the one model that, yeah.
Before you proceed, there is a question by Raphael Greenblatt, and he asks whether the conjecture about teasing that you just stated is weaker than the result by Eisenman and Ware.
Okay, so the result of Eisenman and Ware is different. It's first of all, it's not just considering the perturbation of the model at the criticality. The result of Eisenman and Ware was basically saying that in 2 dimensions, doesn't matter what is what is a parameter of beta and h. As soon as you add disorder, then you have a unique Gibbs measure. You have a unique infinite volume. You have basically a single phase. Unlike the original easy model without disorder, we know that when h equals 0, when you are below the inverse temperature, then you have coexistence of phases, the plus phase and minus phase. So you have a first order phase transition at these points. You have a coexistence of phases. But once you add disorder, you no longer have this coexistence of phases. So this is qualitative. And recently there is work by Jianding and Jiamin Xia, and also later also Pellet, Eisenman, and another, I forgot the other course. So Jianding and Jiamin Xia basically proved that there's always exponential decay of correlations for the spin-spin the boundary effect on the spins decays exponentially as the distance between the boundary and the spin go to infinity. But none of these results address the conjecture we formulate here. So we have to. None of this addresses the conjecture we formulate here, which is about the critical exponent of the magnetization as a function of the external field. So they are basically, so you can, this is a sort of more refined, more specific question and a more quantitative question. I don't know anybody who has sort of worked on this. As far as I know, that this is the first time we formulate this conjecture in the paper with Francesco and Nichols, which I'll mention later.
Okay, I think we can proceed and perhaps continue the discussion at the end if
okay.
needed.
Yeah, so coming back to this renormalization group point of view, there is one model where this sort of heuristic I explained is illustrated in a very clean way, and that is the stochastic heat equation. So this is the stochastic heat equation. So you have the heat equation part, and then you have a noise part, a multiplicative noise, so beta times the solution times the space-time-wide noise. Of course, this is just a formal because this is a generalized function. The space-time-wide noise is a generalized function. U is also a generalized function. So you have the product of 2 distributions, and then that makes it a singular stochastic PD. But nevertheless, let's not worry about this for the moment and just look at it at a formal level. So the renormalization idea that I mentioned, we can make it, we can frame it by redefining by changing the parameters, rescaling the space-time parameters. So I define a new solution, U tilde Tx, which is the original solution, but just on different scales. So 1 unit of time for U tilde corresponds to epsilon to the power minus 2 units of time in the original scale. 1 unit of time in space in U tilde corresponds to epsilon to the power minus 1 units in the original scale in space. So this is exactly this zooming out in space and time called diffusively. So what we can see just by a simple calculation, scaling calculation, is that U tilde satisfies also a stochastic heat equation with multiplicative noise. So psi tilde here is another space-time-wide noise obtained from psi after some scaling, after taking some scaling into consideration. And then what is interesting is that the coefficients in front of the noise gets an extra factor of epsilon to the power of d minus 2 over 2. And now you see that as epsilon tends to 0, as we keep on zooming out onto larger and larger scales, you see that in dimension 1, this prefactor, which can be interpreted as the strength of the noise, blows up when d equal to 1. When dimension equal to 3 or higher, this converges to 0. So this noise disappears. So if we think of the stochastic heat equation as a disordered perturbation of the heat equation, then we see that in dimension 1, the perturbation is a relevant perturbation because the strength of noise blows up on large scales. And in dimension 3 and higher, the strength of noise goes to 0. And dimension 2 is where the strength of noise stays constant. So that's the marginal case. So this is a sort of a simple illustration of the idea of renormalization and the notion of disordered relevances versus irrelevance. And so let me just mention that, so this is an example of a singular stochastic PD, which has been the subject of study by Martin Herrera, the theory of regularity structures, Imkeller, Gubinelli, Perkovsky, the theory of parallel control distributions, and also there is a renormalization group approach by Gubianen. But all these theories apply to models which are disordered relevant. So for the stochastic heat equations, this will be d equal to 1. And when you take the logarithm of the solution of the stochastic heat equation, you get to the stochastic, you get to the KPZ equation. So all these theories are for the disordered relevant regime. In the language of SPDs, it is called the subcritical. Okay, so now coming to the question of scaling limits. So coming back to the idea of disordered relevance, as I mentioned, basically the heuristic is that if you look at in the larger and larger space-time scales, the effective strength of disorder blows up. Or put another way, if I make the lattice spacing smaller and smaller, then the effective strength of disorder blows up. So therefore, a natural way to compensate for this is to send the strength of disorder to 0 at the same time as we send the lattice spacing to 0. If the model is disorder relevant, if the disorder perturbation is relevant, then it should be possible to tune the strength of disorder down to 0 at a suitable rate as a function of the lattice spacing, such that we obtain a continuum model which has non-trivial dependence on disorder as well. So that's the key observation, connecting disorder relevance to the scaling limits and obtain continued disorder continuum models. So starting from this observation, how can we actually go about in constructing such a disorder continuum models for disorder relevant systems? Well, the key quantity is the partition function. So the first thing is to show that there is a suitable choice of the disorder strengths, sending them to 0 as a function of the lattice spacing, such that the partition functions themselves have non-trivial limits with some dependence on disorder. So this was first realized in a seminal paper by Alvarez, Canning, Pastel, where they show that for the directed polymer model introduced in dimension 1+1, if the inverse temperature is scaled like some constant parameter over n to the power 1/4, where we recall that n is the length of the polymer, or in other words, if I scale makes the lattice spacing smaller, then 1/n is the lattice spacing. So under this particular scaling of the disorder strengths, they show that the partition function of the directed polymer converges to a continuum non-trivial limit. And if you vary the starting point of the directed polymer, then the family of these limits actually gives a solution of the stochastic heat equation dimension 1 that I just mentioned on the previous slide. So in the follow-up work with Francesco and Nicolas Zigouras, we made the observation that I just stated, namely that this picture should be valid for disorder relevant systems in general. So that was the result of this paper here. So in that paper, we made this observation and we formulated the general criteria for partition functions of disorder relevant systems to have non-trivial random limits. And we applied this to the partition functions of the pinning model, long-range directed polymer model, and also the random field easy model. So for the partition function of this model, we showed that when do they converge and how the limits can be represented. So the basic idea is to use chaos expansions for the partition function. Okay, so now let me start to go into a little bit technical details of how these continuum limits through chaos expansions can be worked out. So the common framework of the random field easy model as well as the directed polymer model is that the configuration of the polymer or the configuration of the spins basically can be regarded as a family of binary random variables. For the polymer, if you look at every point in every space-time lattice point, then there are only two possible states. Either it is occupied by the random walk trajectory, the random walk trajectory passes through that point, or it does not pass through this point. So you can represent the polymer configuration by a field of zeros and ones. For the easy model, it's either +1 or -1. So again, it's a binary value. So that allows us to put these two models into a common framework where the underlying measure for the lattice spin system is a binary value. In the polymer case, the domain is a space-time domain, while in the Ising case, it's just a subset of the domain in R2 or Z2. So therefore, let's consider a generic domain in RD. So this could be a space-time domain, as in the case of directed polymer. And then we introduce a lattice spacing parameter A. And then so we discretize the domain omega with a lattice spacing A. Again, at each lattice point, we introduce RID random variables with the same assumptions as before. So they play the role of disorder. And then we start with a reference measure. So the reference measure is denoted by P subscript of the domain here, omega A. So that is a reference model. For the directed polymer, the reference model is just a random walk. For the easy model, the random field easy model I introduced before, the reference measure is just the critical two-dimensional easy model. And then what we do is that we introduce a random field perturbation. So this is a reference measure, which is either the random walk or the critical two-dimensional easy model. And then we introduce a random field perturbation, where at every point in the lattice, the spin at that point feels the effect of a magnetic field, lambda omega xh. So for the polymer model, the spins is either 0 or 1 values. And so if the random walk does not pass through this particular space-time point, then this has no effect. But if the random walk passes through a particular space-time point, then you pick up the disorder at that location. For the easy model, it's a ±1, but you can just do a change of variable to transform it into 0 and 1s. Again, this is the partition function. So this is the common framework that unites the directed polymer model and the random field easy model. So the goal is to understand that under what conditions, if we send the lattice spacing to 0, and how can we choose the disorder strength lambda and the disorder bias h, how can we send these to 0 as a function of A, the lattice spacing, such that the partition function has non-trivial continuum limits? So that's a question. And the way we do that is through a polynomial chaos expansion. So here is the way we write out the partition function. So if you go back to the previous slides of what is a partition function? Partition function is simply the average, the expectation of this exponential weight under the reference measure. So if we do that, then we can write it as a product over all lattice points in the system, as a product of all the spins in the system. And every spin has this exponential weight corresponding to the external field. What we have to do is to perform the so-called Mayer cluster expansion, which is suitable for such a discrete lattice models. So basically, we rewrite the exponential as 1 plus the exponential minus 1. The reason we can do this, and this simplifies things, is because sigma x is a binary value. There are only 2 values. So the exponential takes 2 values. So we might as well just replace the exponential by a line, a straight line that passes these same 2 points. So the fact that sigma x takes only 2 values allows us to linearize it, and you just need to identify the correct constants. So in this case, the correct constant here is 1 times sigma x. So now you have a linear dependence on the spins, sigma x. And then the prefactor is just the exponential minus 1, e to the power of lambda omega x plus h minus 1. So then what you can do is that you can expand this product. So if you expand this product, then some brackets will contribute to 1, some brackets will contribute to this psi x sigma x. So depending on how many brackets contributes to the corresponding disorder and the spin variables, we can organize the product as a sum. So that's an expansion. K corresponds to the number of brackets that contributes the psi x sigma x. So that's where you have the K of these psi x's and the K of the sigma x's. And then once you fix a number of these spins that will contribute to the product, then you need to sum over all subsets. So the advantage of this mere cost expansion is that no lattice point will appear more than once in this product. And when you take the expectation only acts on the spins, not on the disorder variables. So these are still functions of a disorder, and they are still RID. So psi x1, psi x2, etc., etc. These are still RID random variables indexed by the lattice. And then you have these k point spin correlation functions taking expectation under the reference measure. So we can check what is the mean and the variance of these psi variables. So it's just the transformation of the original disorder variables. And so you can compute this mean and you can compute this variance. And our choice of parameters ensures that the mean will go to 0 and the variance will also go to 0 because we are looking at a model that is disorder relevant. So this should remind us of the Wiener-Chaos expansion because this is the multilinear polynomial in these ID random variables with some kernel in front. And these ID random variables are indexed by, these ID random variables are indexed by space. So this is really a discrete analog of the so-called Wiener-Chaos expansion, where this is replaced by the differential of a Y noise indexed in space. So the way we can show that this series actually converges to Wiener-Chaos expansion is the following. Basically, what we can do is that we can replace each of psi x here by a Gaussian random variable, a normal random variable with the same mean and the same variance. And furthermore, the normal random variable can be constructed by integrating a Y noise over the cell, over the small cell that is associated with the lattice point. So every lattice point, I can draw a little cell around it. And imagine that there is a Y noise underlying the space. Then I can simply replace psi by the Gaussian random variable, where the Gaussian part is the result of integrating underlying space Y noise, spatial Y noise over this little cell. So therefore, psi x can be replaced by the integral of the Y noise with a bias over this little cell. Now, how to justify this replacement? Well, this is basically a Lindeberg principle. Lindeberg principle says that if you're functional of a bunch of ID random variables or independent random variables, then under certain conditions, you can replace these random variables by normal random variables, and it will not change the law of your functional. For in the case of this, where the functional is multilinear in these independent random variables, this was first studied by Moser, O'Donnell, and Oleskowitz. So this is how to justify this replacement using the Lindeberg principle. Now, once you make this replacement, then the partition function already carries a form that is basically a Wiener-Chaos expansion, because this is simply the k-fold integration with respect to underlying Y noise with a certain bias. And now we have to decide how to choose lambda and how to choose h tilde as a function of A so that this whole series converges. Well, that depends crucially on this k-spin correlation function. So that this is where comes the key assumption for the whole thing to work. Namely that we need to assume that the k-spin correlation function on this on this domain where the lattice spacing is the little a, we need to assume that the k-spin correlation function converges on the scaling to a limit. So the scaling is of the form the lattice spacing to some exponent minus gamma raised to the power of the number of spins under consideration. We need to assume that this k-spin correlation function under this scaling converges in L2 to a limit. The limit must also in L2, be in L2. And this, in fact, implies that if you look at how the spin-spin correlation function in the limit diverges along the diagonal, it diverges along the diagonal according to power law as well. And so the the L2 assumption is satisfied if and only if the exponent gamma here is less than d over 2. So in the physics literature, this assumption is called the Harris criterion for disordered relevance. So in other words, as long as this is in L2, it suggests that the partition function has a disordered continuum limit, or in other words, heuristically, this suggests that the model is disordered relevant, and that is consistent with the Harris criterion. Okay, so yeah, the assumption, so if we look at this assumption again, it's basically saying that the reference model, the reference measure has a power law correlation decay. And that is typical of a model at the critical point of a continuous phase transition. So that illustrates the validity, the range of models that this theory can be applied. Okay, so yeah, so here this is just to say that you just need to choose the lambda and h tilde in such a way that if you collect all the exponents powers of A, they exactly put together, they exactly come together with the k-spin correlation function to give the desired limit. And then you get a bona fide Riemann-Kells expansion. So that is basically how this whole approach works. Now let's come back to how this can be applied to the directed polymer model. So for the directed polymer model, as I mentioned, the domain is now a space-time domain, and the scaling has to be done also diffusively. The reference measure is the law of a simple symmetric random walk, which converges to Brownian motion as the lattice spacing tends to 0. Now the key point, which was a key assumption, has to do with the k-spin correlation function. So in this case, the k-spin correlation function is simply the probability that, so these sigmas are either 0 or 1. So its expectation simply boils down to the probability that the random walk will pass through the space-time point t1, x1, pass through the space-time point t2, x2, all the way to tk, xk. And the random walk starts from the origin. So therefore, it's not difficult to see that this is just a product of the random walk transition kernels. And then for them to converge, you have to multiply by powers of lattice spacing to apply the local limit theorem. So that converges to the heat kernels, the product of heat kernels. And this convergence in L2, if the dimension, spatial dimension of the polymer is 1. When the spatial dimension of the polymer is equal to 2, then you no longer are in L2, and that's where the approach fails. Okay, so once you have this observation, then you can easily figure out what is the choice of the inverse temperature. This ensures that the partition function converges to a limit. So this is a convergence of a single partition function, but you can also vary the starting point of the polymer. So you can have a polymer that instead of starting from the origin, you can have a polymer starting at a different space-time point. And you can even fix the endpoint of the polymer. So you have the starting space-time point, you also have the ending space-time point. So that is what meant by SXTY. You fix the starting space-time point and you fix the ending space-time point. And you can still define the partition function of the directed polymer. So the convergence result that was mentioned also applies to these families of partition functions indexed by these starting and ending space-time points. So that gives you a stochastic process, and at the process level, these partition functions converge. And in fact, this is connected to the solution of the stochastic heat equation. So once you have these family of partition functions and their continuum limits, then we can actually use them to construct the continuum directed polymer model. So remember, the goal is to construct a continuum model with disordered dependence. Partition functions is the first step, but it's very close to the actual model itself, especially for the directed polymer. So for the directed polymer, once you have the continuum limits of the partition functions, how do you construct the continuum model itself? Well, the idea is very simple. We look at the finite dimensional distribution. Suppose that I look at the discrete polymer model, and I look at what's the probability that the random walk or the polymer passes the position x1 at time t1, position x2 at time t2, etc., etc. You'll find that this probability has a simple representation in terms of these families of partition functions. Namely that for the polymer to pass through these points, if you look at the weight, the Gibbs weight associated with such trajectories, it factorizes because they are pinched through all these space-time points. So it factorizes as the point-to-point partition function from this point to this point times the point-to-point partition function here times the next point-to-point partition function, etc., etc. And everything is normalized by the original partition function. Now, since we know that all these partition functions as a process indexed by the starting and ending space-time points converge to a limit, we can therefore easily conjecture that this whole quotient here actually converges to a limit. The limit is simply given by the product of the continuum point-to-point partition functions divided by the continuum point-to-plane partition function. And that makes perfect sense. And in fact, this can be used to define the density of the finite dimensional distribution of the continuum directed polymer. So this is how the continuum directed polymer can be constructed. So there are two papers which worked out all these details by Alberts, Canning-Quastel, which are listed here. Okay, now coming to the easy model, again, the key assumption requires us to identify what is the limit of the k-spin correlation function. So there is an important result by Chelka, Funga, and Izuryov, where they show that actually, if we rescale the spin correlation functions by a to the power minus 1 over 8 raised to the power number of spins, then this converges pointwise to a limit. So this limit is satisfies certain properties. And in this paper that I mentioned before, we extended to convergence in L2 so that we can plug it into the chaos expansion and show convergence. Okay, so the parameters of lambda and h are chosen this way. So it's the scaling has to be a to the power 7 over 8 for the disorder strength and a to the power 15 over 8 for the disorder bias. Then we showed in the paper that with the plus boundary conditions, the partition functions of the random field easing defined this way converges to a continued limit. And the noise in the limit will just be white noise, which is not surprising because on the disordered, on the lattice model, the noise is just the IID indexed by the lattice points. So in the limit, the noise becomes white noise. Okay, coming back to the model without disorder, as I mentioned, Camille Gabin-Newman looked at this model. And what they also proved was that if you, okay, so what the Camille Gabin-Newman looked at was basically the model, the perturbation of the model where lambda is equal to 0. There is no disorder. There is only the external field with a deterministic external field scaled at a constant times a to the power 15 over 8. So what they proved in this perturbation, the external field, deterministic external field perturbation of the model was that if you look at the magnetization field, so this is the magnetization field regarded as a measure, right? Every sigma x is multiplied by delta mass at the point. And then you have to rescale the whole magnetization field by a power exponent of a to the power 15 over 8. So this defines a measure on the domain. And what it proved is that as a distribution, as a generalized function, this actually converges to a limit as the lattice spacing tends to 0. It converges also in the solar space, negative solar space, h minus 1 to the minus epsilon. And later, Foulan and Morat strengthened the result by improving the regularity exponent to the optimal exponent of minus 1 over 8 minus epsilon. So this shows that when there is no disorder, you just perturb according to the external field, then you have a limit for the easing magnetization field as a generalized function. So the question that can you do the same when you introduce disorder as we have done. So this is what Adam will talk about in the next talk. So the paper was posted 1 month ago. So just a subtle point of why it took so long for us to go from the convergence of the partition functions to the construction of the continuum random field easing model itself. The reason was because as we saw for the directed polymer model, once you have the partition functions, you basically can use the partition functions to construct a continuum model. So the partition functions that was needed in the directed polymer context was basically these families of partition functions. So these are families of partition functions with different space-time points. So you can think of it as the polymer restricted to subdomains. Now for the random field easing model, the only thing we have so far is for the original domain, with a plus boundary condition. For that, we have the partition functions, the limit. But if you go to subdomains, the boundary condition is no longer necessarily plus boundary condition. And also the field is a generalized function. So what is meant by boundary condition in this case, when you have a generalized function, take its the value of the generalized function on the boundary of a subdomain. So this all creates problems. And so the approach of trying to construct enough families, a large enough family of partition functions would not work in our context. Instead, the idea is try to compute the Fourier transform of this field phi A. So Adam will talk about this later. Okay, so that more or less is near the end of my talk, and just some comments on possible further directions that has been ongoing, or which one may, or other directions one may explore. So one important direction is to look at the marginal relevance case, marginal relevant case. As I mentioned, for the directed polymer model in dimension 1, it is disorder relevant. But when you go to dimension 2, then it becomes marginal. The disorder perturbation is marginal, marginal. And also, if you look at the stochastic heat equation or the KPZ equation in dimension 2, the theory of singular SPDs also no longer apply. So that makes the marginal case particularly interesting. So there's been some progress for the directed polymer model in the marginal dimension in joint work with Francesco and Nico Zigras. There's also recent work by Gu, Pastel, and Tsai. So you can look up these papers to see what is the current status. So that's one direction. And another direction is was talked about by Hubert Leguin in the one world probability seminar a couple of months ago. So it was joint work with Quentin Berger. And what they considered was directed polymer where the disorder is heavy-tailed. In our case, we assume the disorder has exponential moments, but they assume the disorder is heavy-tailed. And that leads to a continuum limit, which is a Levin noise instead of white noise. So that is also an interesting direction we explore. And another question, of course, is that since the framework is quite general, are there any other models of interest for which we should look at these disorder continuum limits? So the continuum limits are basically analogs of the KPZ equation. You can think of the KPZ equation as one particular example of such a weak disorder continuum limit. And in the SPD context, this is called a weak universality. So this offers a general framework to look at other models which are disorder relevant. And I think that's all for my talk. Thank you.
Okay, thanks a lot, Rongfeng. There has been a couple of questions already in the chat during the talk. So let me now ask all participants if they have other questions. Okay, Amanda Turner, you can read perhaps Rongfeng is asking whether you can give a bit more information about connection between chaos, stochastic heat equation, KPZ equation that you had alluded to at the end.
Okay, so so the stochastic heat equation is partial u over partial t equal to 1/2 Laplacian u plus beta u psi. And the KPZ equation is just the h is equal to log of u plus some constant that diverges with time. So partial h over partial t is equal to 1/2 of Laplacian h plus gradient h squared plus beta psi. So that's the relation between the stochastic heat equation and the KPZ equation is through the so-called Kohoff transformation. So of course, the KPZ equation models the height of a randomly growing interface, and that also is connected to the KPZ universality class.
Yeah. Okay, she was also referring to chaos. Perhaps it's worth mentioning also the link with polymers, because yeah, directed polymer is very close to the stochastic heat equation.
Yeah, that's right. That's right. So through the Feynman-Katz formula, U Tx can be written as, so if we draw the picture here, this is T and X. So through the Feynman-Katz formula, you run a Brownian motion backward in time. And so you just get e to the power of integral from 0 to t of psi t minus s bs of ds of this is respect to the Brownian motion u 0 bt. So we can assume that this is equal to 1 for simplicity. So then if you look at, okay, maybe there is a minus some constant here. So if you look at this expression here, this exponential weight is similar to the exponential weight that appears in the definition of the directed polymer. Namely that we follow a random walk trajectory in the directed polymer and we collect all the disorder along the trajectory. So here the disorder is given by the space-time white noise. And so what we see that we are running a Brownian motion backward in time and we are collecting the noise or the disorder we see along the Brownian trajectory. So in that sense, this is really just the continuous time analog of the directed polymer model. So the correspondence is that the solution of the stochastic heat equation basically corresponds to the partition function. So in the partition function, it was E summation of n from 1 to n of beta omega n of xn minus cn. So that was the partition function. So the partition function is really the analog of the solution of the stochastic heat equation.
Yeah. Okay, thanks. Yeah, Ivan Corwin also gave a comment about the appearance of the chaos series. Yeah, perhaps one can also note that this Feynman-Katz representation at the continuum level is formal. So if one develops the exponential, one gets a chaos series. So which is related.
Yeah, that's right. Yeah, that's right. Yeah. So okay, sorry. Yeah. So if you look at this expression here, the exponential of this integral with respect to the white noise. So psi here is the space-time white noise. So you can actually expand it as into a chaos expansion. The expression here can be written as a Wiener chaos expansion. And that connects up with the polynomial chaos expansion for the directed polymer.
Thanks. There is also a question by Milton, which is an observation that we have results for models that are integrable in a sense.
Okay, that's correct. Okay, we don't need sort of the integrability. Yeah, we do need the strong assumptions on the correlation functions. So the integrability need to be strong enough so that it gives us the case point spin correlation functions, and we need the convergence to be in L2. So for a random walk, of course, this is just the local limit theorem. For the easy model, it depends crucially on the result of Khelkak, Hongler, and Izuryov. So that uses, of course, the integrability of the two-dimensional critical easy model. So that's a limitation of this approach in the sense that we need to work with models so that the models we're perturbing, we have a good understanding of its K-point correlation functions. And we can say that the discrete models that approach the continuum model, the K-point correlation functions converges in L2 to their continuum counterparts. Yes, we need this.
Okay, if there are no further questions, I propose that we all thank Rongfeng for the very nice talk. Yes.
People should be able to clap, allow people to unmute themselves.
Thanks, Rongfeng. Good. And yeah, I don't know if there is supposed to be a pause, but otherwise I think we can proceed to the next talk by Adam. Adam are you here? Okay, hi Adam.
All right. Let me share my screen.
Good. Can you put it? Okay, great.
Is it in full screen?
Yeah, that's in full screen. We can see. Okay, so it's a pleasure to introduce Adam Bowditch, which is now at University College Dublin, and who's going to talk about the two-dimensional continuum random field Ising model introduced by Rongfeng in previous talk. You can go, Adam.
Okay, thank you very much for the introduction and the invitation to speak here. And thank you also, Rongfeng, for giving this first talk. So as Rongfeng and Francesco have said, I'm going to be speaking about a sort of continuation of this previous talk, in that I'll speak about a specific disorder relevant model, which is the two-dimensional random field Ising model. So to begin, I will just go over a few of the basic facts of the Ising model, that some of which Rongfeng has already covered, before I move on to constructing the continuum magnetization field and discussing how this continuum disordered model relates to the continuum model in the absence of disorder. So the Ising model is this classic model of magnetization in which we fix our domain omega, and we then discretize this domain using a lattice with lattice spacing A. And then the Ising model is this described by this law, which is a law over spin configurations. So for each vertex in our discretized domain, we assign either a plus or minus spin. And the measure is exactly given here, and it's weighted so that it typically favors spin configurations where we see alignment between neighboring spins, okay, given by this weight, this exponential weight here. And as in the talk by Rongfeng, we'll typically consider plus boundary conditions, which are ensured by this product here, and Z denotes our partition function. So a key thing about this model is that we have this parameter beta, which is our inverse temperature. And as we increase the value of beta, we favor more and more these configurations where we see alignment. And as Rongfeng discussed, this leads to a phase transition. In particular, we have a critical value of beta, such that for large values of our inverse temperature beta, we see that the average magnetization converges in the scaling limit to a positive value, whereas for small values of beta, this term converges to 0. And a particular, this is only in dimension 2 and above. In dimension 1, this was studied, and there's no phase transition in dimension 1. Okay, and one thing that this particularly shows is that at low temperature, we see long-range correlations in the model. So this is where beta is large. But if we take beta small, then we see that the correlations in the model decay. Okay, and dimension 2 is a particularly important case for several reasons, and one of which is that at critical temperature in dimension 2, there's a long-standing conjecture that a lot of the interesting objects in the model should have some sort of conformally invariant scaling limits. And this has been studied a lot in recent years, and there's been a huge amount of recent progress, largely instigated by some work of Stanislav Smirnov, who introduced the idea of fermionic observables. And this has led to a lot of recent work, and one particular result, which Rongfeng also mentioned, is this result of Chaukak-Ongler and Izarov, who showed convergence of the K-point spin correlations. And this is going to be a particularly important result for this talk. So let me speak about this a little bit in detail. So what this result shows is that if we take, say, K points in our domain, and we look at the correlation between the spins at these points, then with this power law scaling, this term converges to what's actually a conformally invariant scaling function. Okay, and in particular, this has been extended, and one could show that this convergence can be extended to L2, which is something Rongfeng also discussed in his talk. Okay, and in particular, this scaling of a to the minus 1 over 8 is going to be very important and come up throughout the talk, precisely for some of the reasons Rongfeng mentioned, and we'll see this in practice shortly. But the main object of interest in this talk is going to be the magnetization field. So this is a random distribution that you find by taking a sum over the spins in our discrete domain and having them against Dirac masses, and then scaling this appropriately. And we'll see that this is indeed the correct scaling, so that we see some sort of non-trivial scaling limit for this object. And in particular, this is a random distribution, so we understand this object by testing against smooth functions. And a few years ago, it was shown by Camille Gavin and Newman that at critical temperature in 2 dimension, this random distribution converges in law to a continuum random distribution, which also satisfies some conformal invariance relations. Okay, and so the main question that I want to speak about in this talk is whether this convergence here for this magnetization field is influenced by the presence of disorder. So first, let's recap how we're going to introduce disorder into this model. So there are several ways that this can be done. And the way we're going to introduce disorder into the model is by introducing site disorder. So we take an IID family of random variables, which we'll assume are centered with some exponential moments, and we'll define the random field Ising model for fixed copies of this disorder omega as this change of measure from our critical Ising model. And in particular, we're just introducing this random external field here, which is just tilting the configuration to have this slight additional preference towards the random external field, as well as seeing this preference for having alignment in neighboring spins. And in particular, we can break this down. We have a fixed external field H and a disorder strength lambda. So as we increase the value of lambda, we favor configurations of spins which want to align with this disorder. And as we take lambda closer to 0, we're reducing the effect of this external field. And exactly what we want to understand is whether for a suitably small value of lambda, we still see the same qualitative behavior in the critical Ising model, or whether there's a significant change. In particular, we want to ask the questions, do we still have the phase transition? Are the spin correlations changed by the presence of this disorder? And also, do we still see convergence of this magnetization field? Okay, so as was mentioned in the previous talk, there's a result of Eisenman and Wehr, which says that indeed dimension 2 is an important dimension for this model, in the sense that in dimension 2, the model is disorder relevant, by which we mean that for any disorder strength lambda, and almost every instance of the disorder omega, we have a single phase. So there's no transition, as we saw in the absence of disorder. But really, dimension 2 is somehow critical in this sense. So it's also been shown that in dimensions 3 and above, for suitably small values of the disorder strength, one still sees a phase transition. Okay. So from now on, we'll really be working in dimension 2 at critical temperature, which is this disorder relevant regime for the Ising model. Okay, so a key object of interest are the spin correlations. So this result of Chalkak-Onglu and Izhirov showed that at critical temperature, the spins decay at a rate around a to the 1/8, where A was our lattice spacing. So a very natural question is to ask how the decay of spin correlations is affected by this external field. And there have been quite a few recent results in this line by the likes of Chatterjee and Eisenman and Peled, and more recently Ding and Zia, and also a result similar to this slightly later by Eisenman, Harel and Peled, which culminates in the fact that the spin correlations with disorder decay exponentially in the lattice spacing. Okay, there are still many more interesting questions that can be asked about the spin correlations, but for the purpose of this talk, I want to move on to speaking about the magnetization field. Before that, let me just recap something that Rongfeng was discussing, which is that we know this model is disorder relevant, and a key thing we'd hope with a disorder relevant model is that we may be able to scale the disorder strength and in this case also the external field H, tuning them to 0 in such a way that we see some sort of continuum scaling limit. And what Rongfeng showed with Francesco Caravana and Nicole Sigurus, and was discussing in the previous talk, was exactly that if we look at the disordered partition functions, then at this scaling written here, one can perform a polynomial chaos expansion and use this to show that under this suitable scaling, these disordered partition functions converge in distribution to a Wiener chaos expansion. Okay, and in particular in this chaos expansion, we see that the disorder is being manifested as this copy of white noise, and we're still seeing the spin correlation function that comes from the pure Ising model, like the Ising model without disorder, coming through into this scaling limit. Okay, so this just shows how important these spin correlations are, and really that they're going to be characterizing a large amount of this model. Okay, and as Rongfeng briefly discussed in the previous talk, one would like to construct more interesting objects from the more interesting continuum objects, that is, from these partition functions, including the continuum magnetization field. However, for some technical reasons, this is incredibly challenging. It would require somehow understanding the partition functions on somehow arbitrary domains with arbitrary boundary conditions, and it's very unclear how what this really means in this this limiting sense.
Adam, just a question.
Yep.
This is not the approach that you are following, but just out of curiosity, what are the available results on the correlation, on the spin correlations for more general boundary conditions than just plus? Are there?
So I'm not sure on the exact results, but certainly Chakakonglu and Ismarov proved slightly more general results that you could have sort of alternating, some finite segments of the boundary plus finite segments of the boundaries minus, and this sort of thing. I think it also holds for free boundary conditions.
Okay.
So yeah, reasonably, most of the results I'm talking about here should extend to slightly more general boundary conditions than just plus boundary.
Okay, thanks.
Okay. Okay, so the question I want to really discuss here is whether the magnetization field to this random distribution still converges in law in some sense under the influence of a diminishing random external field. So if we tune our disorder in the same way as we were for the partition functions, do we still see some continuum limit? And the way we're going to study this is by studying the quench law of the magnetization field. So if we fix a copy of disorder omega, I want to define this quench law mu as the law of this magnetization field. So not only do I want to understand the continuum limit of this object, I want to understand how the disorder is going to influence it in this limiting case. And as we saw with the partition functions, the disorder is somehow being represented by this white noise. So one can take a good guess that should be relevant in this case as well. So what we're going to do is consider not only these this quench law, but we're going to consider an approximation of white noise that we'll shortly see is the right approximation that gives rise to this this white noise in the limit. So a key point that I need to briefly mention is that both our magnetization field and this white noise approximation are random distributions. So before we start speaking about their convergence, we really need to set up a suitable suitable space in which to consider them. And for this, we're going to consider a class of Bezov-Holder spaces. Now, I won't go into a huge amount of detail into these spaces, so don't need to worry too much about these, but this is the space we'll be considering these random distributions in. And the key point we're really going to use about these spaces is that there's a very nice alternate construction of these spaces by Furlan and Morat, in which they construct an alternate version of these spaces using a multi-resolution analysis. And I'll discuss this more slightly later. Okay, so I don't want to dwell on the details of this too much, but for those of you who are interested, these are the distribution spaces we'll be working in. Okay, so this brings me on to the main theorem. So the main theorem of this article is that if we fix our disorder strength to be strictly positive and take this external field H, then in the suitable Bezov-Holder spaces, we see that the joint law of this white noise approximation and the quench law of the magnetization field indeed converge to a pair, which is a copy of white noise and a continuum law mu w. Okay, in particular, if we take a fixed copy of the white noise w, then this uniquely determines mu w as a probability measure on this Bezov-Holder space C alpha log. Okay, And one, so there's a second result that I'll also speak about, which is discussing how this disordered probability measure relates to the limiting probability measure in the absence of disorder. So our second result shows that if we take, or for almost every copy of the disorder, this disordered continuum limit mu w is in fact singular with respect to the law of the continuum magnetization field constructed by Kamiokava and Newman. And this shows several things, one of which is that somehow we could have taken a slightly naive approach to constructing this continuum measure, which would be to consider convergence of the Radon-Nikodym derivative. So we consider mu as a change of measure of our reference measure, which is the critical, so the law of the magnetization for the critical Ising model. And one thing that this second result shows is that would have been it would have been hopeless to try and define the continuum limit in that way. And I'll discuss this result slightly more later. Okay, so for the rest of the talk, what
Adam, sorry.
Yeah.
There is a question by Milton about the singularity of this measure. Is this only when h is different from 0?
No, still true for h equals 0, true for any h. Yeah.
Yeah, no, the convergence, but the singularity.
Yeah, it's true for any h.
H is, yeah. Okay.
Yeah, and in fact, I didn't mention here, but one can in fact take both lambda and h to be functions from the domain omega onto the positive reals and reals respectively. So we don't even need to take lambda and h constant, but we can take them to be functions so long as they're sufficiently regular.
Okay, just to remind, yeah, h is the disorder mean, while lambda is the disorder standard deviation.
Yes, yeah.
Okay. So as long as there is disorder in the limit. You have
Yeah, so we will require that lambda's kind of strictly positive everywhere if it's a function, but actually that could potentially be relaxed. But I'll, for the purpose of this talk, I want to consider lambda and h just constant so that it's slightly less technical. And I might comment in a few points where this changes. But yeah, thank you. Okay, so for the remainder of this talk, I really want to speak about how we go about proving these two results and the ideas behind it. And so I won't go into too much detail, but I just want to highlight really the main points involved in proving these two results. So let's start off with the first result, the convergence. So a sensible way to understand the magnetization field is to study its quenched characteristic functions. Okay, so that's what we've got here. We understand the magnetization field by testing with a smooth function. So if we introduce a smooth function phi and test our magnetization field against this phi, we can consider the characteristic functions of this random variable. And pretty much just by definition, one can see that this quenched characteristic function can be written in terms of a ratio of partition functions, where this smooth function phi we've introduced really just appears in the mean of the external field. So exactly, this just follows from the fact that we defined our random field model as sort of a Gibbs change of measure of the critical Ising law. And so what this equality really says is that if we want to understand the law of our magnetization field, we can in fact study this by studying the joint distribution of partition functions with changes to the external field, changes to the deterministic part of the external field. Okay, and in particular, we just need to consider families of partition functions where we have this extra imaginary part of our deterministic external field. So what we would perhaps hope to be the case, similar to the case that Rongfeng studied with Francesco and Nikos, is that one should hope to be able to do a polynomial chaos expansion using these same techniques, and indeed just see this this imaginary term coming into our chaos expansion here. And so in order to, and so this is indeed true. So in order to actually prove convergence of our finite dimensional distributions, we want to instead consider finite families of these polynomial chaos expansions and show that these converge to sort of finite families of Wiener chaos expansions. And similarly to the one-dimensional case where you consider just a single partition function, this can be studied using a Lindeberg principle, in which we swap out the disorder random variables one by one with a Gaussian random variable. And by doing this in the right way, using a copy of white noise, one can really couple these processes together and see that indeed the white noise we obtain in the limit of these partition functions is indeed the same as the white noise we're obtaining from these approximations of our Wiener chaos, of our white noise, sorry. Okay, so that's just the kind of main idea for proving the convergence of the finite dimensional distributions of these laws. So the other key part of the proof of this first result is to prove tightness of these laws. And as I said before, this really is reliant on this this result of Ferland and Morat, who developed these Bezoff-Holder spaces through a multi-resolution analysis. And in the same article, they used this construction to develop a tightness criterion for random fields, which they then used to strengthen the result of Camier, Gabin, and Newman of the convergence of the magnetization fields in the absence of disorder to optimal regularity. Now, when we have this random external field, there's some extra technical input that's needed to adapt this very slightly. But really, the framework that they've set up here was very suitable for this construction. And what we want to show to prove tightness boils down to proving one very key estimate, which is to bound moments of our total magnetization. So what we want to show is that if we fix our lattice spacing at 1 for now and consider the total magnetization appropriately rescaled in some n by n box, then we want to show that this has finite Pief moments uniformly over the size of this box, a domain containing this box and boundary conditions on this domain. And this isn't completely immediate, and in fact, without disorder, this was shown by using some very classical techniques, including the FKG inequality and the relationship between the Ising model and the FK Ising model. And these two techniques in particular aren't directly applicable to the disordered model. So there's some extra technical input required in order to prove these sorts of bounds in the disordered model. But one can indeed obtain suitable bounds on these Pith moments of this rescaled total magnetization. Okay, so that's all I want to say about the convergence result. And so what I'd like to move on to is spending a bit of time talking about this singularity result. So this was the statement that for almost every copy of the disorder, so in the limit, this copy of the white noise, the disordered continuum limit mu w is in fact singular with respect to the law over the continuum magnetization field without disorder. Okay, so let me first explain some of the basic intuition as to what's happening here and a few of the interesting aspects to this result. So firstly, the intuition one can build in, and exactly what we're going to build the heuristic argument for proving this result, is that somehow the system can be split up into subdomains. And if these subdomains behave in suitably independent way, with just this random tilting coming from the disorder, if this idea holds on a finer and finer scale as we refine our mesh, then this creates a singularity. So this is the intuition as to why the model should be disorder relevant, and it's also the heuristic that we're going to use to try and prove this singularity, as we'll shortly see. So another point is that this singularity is somehow a local phenomenon, in the sense that if we take some subdomain and consider the magnetization field restricted to this subdomain, then we'd also see that the law of this object is singular with respect to the corresponding restricted magnetization field without disorder. And this comes back to this heuristic that somehow the system's being split into these subdomains, and the singularity is really occurring on all subdomains on finer and finer levels as we refine the level more and more. So another point that is perhaps quite unusual is that if we, instead of considering the quenched measure, take an average with respect to our disorder and consider this averaged quenched measure, then this is in fact absolutely continuous with respect to the case without disorder. And this is in fact a property that's quite common in these sorts of disorder relevant models. In particular, it holds for similar models such as the directed polymer model that Rongfeng was talking about in the previous talk, and also the disordered pinning model. And in fact, one of the key techniques that we're going to be using in our singularity argument is a technique that was first developed for the disordered pinning model. And it's called a fractional moment technique. And I'll be going through this very briefly, but firstly, I should say that there's one very key difference between the techniques for some of these other models and the techniques we'll employ, which Rongfeng also spoke about very briefly, which is that in some of these other models, you can construct a continuum disordered limit in a very nice way from the partition functions, which really lends itself very well to these fractional moment techniques and other techniques in this field. In our case, we don't have such a nice representation that will allow us to do this quite so easily. So we're going to have to employ a slightly more delicate approach. Okay. So let me start explaining our strategy for approaching this singularity. So, as I said, somehow we want to think that the system's being split into these subdomains, and if the random tilting on these subdomains is strong enough on a finer and finer scale, then we should see a singularity emerging. So we're going to partition our domain, which for now I'm just going to take to be the unit box, just to keep things slightly simple. So we'll partition this domain into some n squared boxes, bij, n. And then we'll define some random variables, phi ij, as the total magnetization on this partition box bijn, and wijn, the average white noise on this partition box. So our hope here is really that we're splitting our domain into this partition, observing the magnetization on these boxes, and each of these magnetizations should have this random tilt exactly coming from the somehow averaged white noise on the same box. And the approach we want to take is to show that if we condition on these random variables, then our Radon-Nikodym derivative converges as we refine our partition to 0. Okay, so the key problem with trying to take this approach is exactly as I mentioned before. We don't have a nice representation of our Radon-Nikodym derivative. And this makes this object quite challenging to deal with. We do, however, have a very nice representation of the mesh discretized version of this Radon-Nikodym derivative. So, and that's given exactly by this equation here, where we have this partition function and this exponential factor. Okay, so what we would like to do instead is work with the discrete version, where we indeed have this explicit representation. Okay, so we'll consider these random variables Q and A, where we just replace everything in Q by its suitably mesh discretized version. Okay, so here we have this derivative here, and these functions are just these suitable discretizations of our average magnetization field and the averaged white noise on these boxes. So what one wants to do is basically say that a QNA is a suitable approximation of QN, and instead show that as we take a scaling limit as A goes to 0, then N tends to infinity, these QN converge in distribution to 0. However, this is actually quite a subtle point in the argument that it's not actually obvious that this mesh discretization is a suitable thing to consider here. So in our proof of convergence, we showed that the disordered limit converges to a continuum disordered limit, and Kamiogaban and Newman showed exactly that without disorder the same occurs. But this doesn't imply convergence of our Radon-Nikodym derivative, and this makes things slightly complicated. So one does need to work a bit harder to prove that this is in fact a suitable representation, suitable approximation of the continuum object. and in fact, one key property we want to show in order to justify this is to show that if we fix the level of the filtration, so if we fix n, then this family indexed over the lattice spacing is a uniformly integrable family. And what this essentially guarantees is that if we have that these guys converge as a tends to 0, then they should converge to the correct density, which is what we want. Okay, I don't want to speak any more about this, but so let's move on and suppose that indeed these discretizations are a good approximation, which indeed they are, with some slight adjustments. So so we want to show that Q converges to 0 in probability as first A goes to 0 and then n tends to infinity. Now we know that the expectation of Q with respect to this average quenched law is 1. And if indeed we do have a singularity arising as we should expect, Q should be typically very close to 0, and then on very rare events, Q should be very large. So a potentially sensible thing to show in order to show that this does indeed converge to 0 is to show convergence of these fractional moments. And so the way we're going to do this is we're going to introduce a density in order to sort of dampen the value of Qn on these very rare events where it's very large. So we'll introduce this function Q, introduce this function G, which we want to think of as a change of measure for both the efforts for the joint law of the disorder and the spins. And we want to use this to really weaken Q on these extreme values. So we look at our fractional moments and introduce both Gn to the half and Gn to the minus a half into this equation, apply Cauchy-Schwarz, and this splits up our fractional moment into these two parts. One where we are going to consider this kind of change of measure argument, which requires that G is sort of killing off Q on these large values, and one which is going to require G not to be too small. And ultimately what we're going to want to show, or what we're going to want to do, sorry, is choose this function Gn in a suitable way such that this first expectation converges to 0 and this second expectation is bounded. And this is really the most model specific and challenging part of this argument is finding a suitable function G such that one has these two properties. So let's go through how one does this and why this is challenging. So to start off with, in order to do this previous argument, we required that G was positive, and in particular, we want it to be a function of these random variables, the phi ijna and the wijna. Okay, and that was so that we could perform this last step of this last bound here. So it should be equality. So we required that G was measurable with respect to this filtration, i.e. G is a function of this family of random variables. And our intuition is exactly that we want Gn to be relatively moderate so that this second term is bounded, but we need it to be very small when our Radon-Nikodym derivative is very large in order to indeed show that this first condition holds. Now, our intuition was exactly that Gn should be used as a change of measure for the joint law of the disorder and the spins. However, there's nothing in our argument that really requires this to be the case. And in fact, we're going to take a slightly different interpretation, where instead we're going to use the derivative here in red as a change of measure, not for the joint law of the spins and the disorder, but rather if we fix a copy of the spins, we're going to use this as a change of measure on the disorder. Okay, and ultimately what we want to then do is manipulate this into this into some nice form where we have this sort of expectation of a Gn, which we then want to show converges to 0. Okay, so let's first start talking about this this change of measure for the disorder. So we have this very nice explicit form of d mu omega by d mu. And for now, I'm going to ignore this first term involving the partition function and really focus on this exponential factor. This is where we're seeing the interaction between the spins and the disorder. So this is where we should expect this tilting to really have a strong effect. So what we'll do is we'll fix our spin configuration and use this exponential factor as a change of measure for the disorder, defined exactly here. Okay, where now z is some partition function which should depend on the spins. In fact, in this case, it doesn't. It's actually independent of the spins, which is very helpful. But exactly, we'll define a new measure on the disorder by this. So this is a random probability measure over our disorder. Now, in order for this to be useful, we really need to understand what our original measure on our disorder was. So in our original proof of convergence, our restrictions on the disorder were quite weak. We only required that we had this IID family of random variables which were centered with exponential moments. And regardless of the finer details, we saw the same limiting object. So in fact, we have quite a lot of freedom to choose the law over our disorder, so long as it fits into this framework. So what we'll do is we can take the disorder to be independent standard Gaussians with respect to our original law on the disorder. And very conveniently, what this change of measure then does is act as a shift on the disorder, where we maintain the fact that our disorder is IID Gaussians with unit variance, but under this change of measure, the disorder at site X now just has this slight shift in its mean towards lambda a to the 7/8 sigma x. So we're indeed just seeing this very slight shift in the law of the disorder coming from the spins. Okay, and indeed, once we deal with the partition functions in a suitable way, which I won't go into, one can indeed relax change this first condition that we wanted to show into showing that this function Gn, which we haven't even constructed yet, converges to 0 in expectation. Okay, so this brings us back to exactly choosing this function Gn, which, as I said before, is really model specific, and there's not necessarily an obvious way that this function G should be chosen in this argument. And on top of that, one should really choose G together with the filtration. So I chose the filtration at the beginning of the construction, but really we haven't used much of the detail of this filtration yet, and one should really choose Gn in combination with this in the right way. So our intuition on this this function g was that typically we wanted it to be close to 1, but we wanted it to be very small when q was large in order to weaken the values of q on these extreme values. And the way we're going to do this is take two deterministic sequences converging to infinity and choose g to be this negative exponential, where this random sequence xn is going to be an approximation of q. So exactly when q is large, we'd like x to be large, which makes g very small. And if x is sort of moderate or small, then we indeed see that g is equal to 1. So this somehow fits in with that intuition that we wanted to build in. And one could just take x equal to q, and this would be fine, but this isn't necessarily the easiest object to work with. So instead, what we're going to do is we're going to take the derivative here in red, which we have this explicit form of, and every time we see a spin sigma x, we're going to replace it by block spin. So we'll replace it by 1 if the total magnetization on that block was greater than or equal to 0, and -1 if it's less than 0. And similarly, in the same form, we'll replace our disorder by the averaged white noise on this block. And our hope is that this approximation will be good enough in order to satisfy these properties of Gn that we were looking for. So in particular, this choice of Gn gives us this very nice function xn, which is an exponential of a Gaussian. So I can't stress enough here that this ability to choose the disorder variables to be Gaussian is incredibly valuable here, and it's really a very important part of the argument, and it allows us to really find a suitable function x here, which we can work with explicitly. So in particular, this Gaussian in red here is very nice. So under the original law, this is centered, whereas under this perturbed law, so for the fixed spin configurations under p sigma, this is still Gaussian, but now we have a slight tilt to the mean, and this is really quite crucial. And this is what's going to build our singularity. Okay. So skipping a little bit of the technical details, one can examine xn using Gaussian tail estimates and other techniques. And with a bit of work, the proof really then reduces to understanding certain properties of the EC model without disorder. And the key estimate that we would need to show is exactly this one here. So if we take the total magnetization on the partition box Bij and A and take an appropriate rescaling of this, then this somehow we would like to think should have some reasonable scaling limit. So this should be some sort of non-trivial random variable in the limit as A tends to 0. So we would hope that we should be able to have some sort of law of large numbers, which exactly shows this result, since we have n squared of these objects and only n to the minus 15 over 8 scaling here. Okay, and the key point here that we don't have is that these aren't independent. So one needs to work a little bit harder to gain this independence, and this can be done using a Rousseau-Seymour-Welch type argument. So if this large square here is our domain, and these smaller squares are our partition, what we do is we group these partition boxes into these groups of 9 and use an RSW argument to say that, well, with positive probability independently of the configuration outside this 3x3 block, we have a plus Ising loop in this annulus. And what this means is that we can take a positive fraction of our partition boxes that can be stochastically dominated below by the total magnetization on one of these boxes where the plus boundary has been pushed out to the exterior of this 3x3 block. Okay, and this gives us a positive fraction of these random variables, which we can make essentially independent, and indeed prove this sort of law of large numbers result, which is the final and main estimate that we need in order to prove this singularity. Okay, so I think I'm kind of running out of time. Just wanted to briefly mention a few key open problems, which one of the main difficulties in this was that we didn't have an explicit construction of our continuum law. And one of the key things we'd like to do in the future, which would be very valuable, is having some sort of explicit construction, perhaps in terms of some loop representation, which does in fact hold in the case without disorder. Okay, so thank you. I'll stop there. And, thank you for listening.
Okay. Thanks, Adam, for the talk. I ask participants if they have questions or comments. I have a question. In the main result, you mentioned that the limiting random measure is uniquely determined by the realization of the white noise, almost surely.
Yeah.
Could you comment how you prove this?
So this really comes down to the Lindeberg principle. So we can start off with a copy of white noise and use this to define the Gaussian random variables that we're going to swap in to the chaos expansion, and this couples everything in the right way that we build up this continuum measure with the disorder being represented by this limiting white noise.
Okay, so this determines gives I mean, it's an implicit mapping, but still determines the uniqueness of.
Yeah.
I see.
I think it's basically we know the joint realization of the law of the whole family of partition functions, where the other partition functions is a result of introducing these imaginary fields.
Mm-hmm.
So if you know the Fourier transform with respect to test functions simultaneously for all possible large enough family of test functions, then you know the field.
Yeah, I see. And this is determined by the realization of omega.
Yes, that's right. Because everything, all the partition functions are expressed as chaos expansion with respect to the white noise.
Ivan, does anybody there have a question? Your child wants to make a comment.
Yeah, but it's all nonsense as far as I'm concerned. What are you saying about?
So, Adam, may I ask a question?
Yeah, of course.
Yeah.
So, I was thinking about this singularity with respect to the original measure. So, can you compare with the case of the polymer? Because in the polymer, I think it's not singular, no?
I thought it was. Maybe Rongfeng would be a better person to comment on that.
Singular.
Singular.
It's singular.
It was singular too.
Yeah.
But when you average out the noise, if you look at the crunched average measure, the crunched average measure is absolutely continuous with respect to the Wiener measure.
Okay.
I think in the polymer setting, mean, the polymer moves like a diffusion with the unit diffusion, but with a distributional drift, which is why it's singular.
Okay.
It's out of the Cameron-Martin space.
Okay. Okay. Thank you.
Okay. Do you have other questions, comments? Okay. If not, I think we can thank Adam and also Rongfeng for the talks. And so I propose to make an applause clap. Everybody is allowed to.
And now everybody is allowed to unmute themselves.
Okay.
So.
Thank you.